Okay. Okay, welcome to the linear algebra class. And okay, before we consider this, here is the theorem 3.6. Okay, suppose that I have any m by m matrix A, then by by means of some elementary row operations and some column operations, the matrix A can be transformed into a matrix of this form where I sub R denotes an R by R identity matrix and O1, O2, O3 are all zero matrices. Okay, so before we consider some reasoning, so let us consider some example. So suppose that I have this A matrix. Okay, then by some row and column operations, A can be transformed to some matrix of this D. Okay, so let me check this. So I have a matrix A given by 0, 2, 4, 2, 2, 4, 4, 4, 8, 0, and 8, 2, 0, 10, 2, and 6, 3, 2, 9, 1. Now here I have 0 in the first row, first column. So what I need is I need to interchange this first row with any other row, say second row. Then the matrix will become a 4, 4, 4, 8, 0 in the first row, 0, 2, 4, 2, 2, 8, 2, 0, 10, 2, 6, 3, 2, 9, 1 matrix is obtained. Now, given this new first row, when I look at the entries of this matrix, I mean of the first row, they are all multiples of 4. So let me multiply a quarter to the first row. Then the first row of the matrix becomes 1, 1, 1, 2, 0, and 0, 2, 4, 2, 2, 8, 2, 0, 10, 2, 6, 3, 2, 9, 1. Now, given this matrix, if I multiply negative 8 to the first row and then add it to the third row, then the other rows are not changed. But if I multiply negative 8 to the first row, then you get negative 8, negative 8, negative 8, negative 16, and 0. If you add those numbers to the third row entries, then the numbers will become 0, negative 6, negative 8, and negative 6, and 2. And the fourth row will be unchanged. And then if I multiply negative 6 to the first row and then add it to the fourth row, then the matrix becomes 1, 1, 1, 2, 0, 0, 2, 4, 2, 2, 0, negative 6, negative 8, negative 6, and 2, and 0, negative 3, negative 4, negative 3, and 1. So when I look at this matrix, the first column is now 1, 0, 0. Okay, now I go to the second column and I want to look at the entry in the second row, second column. So the second row, second column entry is now 2. So to change this number to 1, let me multiply 1/2 to the second row of the matrix. Then the matrix becomes 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, -6, -8, -6, 2, 0, -3, -4, -3, and 1. And then here, if I multiply 6 to the second row and then add it to the third row, okay, then the matrix becomes 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, 0, 4, 0, 8, and then fourth row, 0, -3, -4, -3, and 1. And then if I multiply 3 to the second row and then add it to the fourth row, the matrix becomes 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, 0, 4, 0, 8, and then 0, 0, 2, 0, 4. So at this point, the first row below 1 is zeros, and in the first column, the first column becomes 1, 0, 0, 0, and in the second column, this 1, and then below this 1 I have 0 and 0. I don't care about the 1 above the 1 in the first row, okay? So I don't care about this 1 at this point. I will handle that value later, okay? But I will use this 1 in the second row, second column, and using that value, I change all the numbers below to 0, okay? Now I go to the third column. So I have 4 here. So let me multiply 1/4 to the third row. Then the matrix becomes 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, then 0, 0, 1, 0, 2, and then 0, 0, 2, 0, 4. Okay? And then let me multiply -2 to the third row and then add it to the fourth row. Then the matrix becomes 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, 0, 1, 0, 2, 0, 0, 0, 0, 0. So at this point, the matrix has 1, 0, 0, 0, 1, 0, 0, 1, 0. Okay? And then in the fourth column and the fifth column, the fourth row entries are all zeros. I mean, these two numbers are zeros. So I stop there, okay? And then I will try to eliminate the numbers above these numbers. I will change these three numbers to 0, okay? But when I handle those three numbers, I will go in the reverse order. I mean, I multiply -2 to the third row and then add it to the second row. Then the matrix becomes 1, 1, 1, 2, 0, 0, 0, 0, 1, and -3. And 0, 0, 1, 0, 2, 0. Okay? Now, to change this value to 0, let me multiply -1 to the third row and then add it to the first row, then you get 1, 1, 0, 2, and negative 2, 0, 0, oops, not 0, 0, here, oops. I should have 1 here. So 0, 1, 0, 1, negative 3, 0, 0, 1, 0, 2, and zeros. So when I look at the third column, it is now 0, 0, 1, 0. So you have only one non-zero value 1 in the third row, and all the other entries are zeros. Okay. And then to change this value to 0, let me multiply negative 1 to the second row and then add it to the first row. Then the matrix becomes 1, 0, 0, and 1, and 1. And then you get 1, 0, 0, 1, 0, 1, negative 3, 0, 0, 1, 0, 2, and zeros. So now I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay. Then, so these three columns are now independent. Okay. At this point, okay, I will perform now column operations. Okay, so up to this, I just performed row operations. Please remember that. Okay, and then now let me consider some column operation. So for instance, let me multiply negative 1 to the first column and then add it to the fourth column. Then the matrix becomes, so 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0 are not changed. But if I multiply negative 1 to the first column and then add it to the fourth column, this 1 in the first row becomes a 0, and all the others are not changed. And then if I multiply negative 1 to the first column again, and then add it to the fourth column, then this 1 will become 0, while the others are not changed. Okay. Now, let me multiply negative 1 to the second column and then add it to the fourth column. Then this 1 will become 0. So you get 1, 0, 0, 0, 0, 0, 1, 0, 0, negative 3, 0, 0, 1, 0, 2, and zeros. Okay. So at this point, the fourth column now becomes just the 0 column. Now let me multiply 3 to the second column and then add it to the fifth column. Then matrix becomes 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 2, 0, 0, 0, 0, 0. Now let me multiply negative 2 to the third column and then add it to the fifth column. Then the matrix becomes 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, and zeros. So now I have 3 by 3 identity matrix here. And then I have some zero matrix, some zero matrix, and some zero matrix here. Okay, so the shape is I sub r. So I sub 3, 3 by 3 identity matrix on the upper left corner. And then we have zero matrix, 3 by 2 zero matrix, 1 by 3 zero matrix, and 1 by 2 zero matrix. So we arrived at this format, right? So let me write down like this. So we have 1 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 0, so that this shape is the 3 by 3 identity matrix, and O1, O2, O3 here. O1 is 3 by oops, O1 is 3 by 2 identity matrix. O2 is 1 by 3 identity matrix, and O3 is 1 by 2 identity matrix. And in the upper left corner, we have 3 by 3 identity matrix, I sub 3. Okay? So, given any matrix, if I perform some row operation, okay, you arrive at this matrix, right? You arrive at this matrix, and then after that you perform some column operations, and then eventually you derive some matrix like this, and that is called D in the theorem. So we arrive at this D matrix where in the upper left corner we have the identity matrix, and then we have these zero matrices here, and those will define the matrix. So given any matrix, by performing some elementary row or column operations, you can transform your matrix into a D matrix which has some identity matrix in the upper left corner, and all the others are zero matrices. Okay, and if you check the proof, you will see that any matrix can be transformed to a D matrix like this. Okay. Okay. So given any matrix A, by performing elementary row operations and column operations, we can derive a D matrix, right? Now, let me go back to this example one more time. Given A matrix, I performed the first step was to interchange the first and second rows of A to get this new matrix. Now, this new matrix can be written as some elementary matrix times A, say E1, right? And what is E1? E1 is the elementary matrix, okay? So E1 is elementary matrix obtained from the identity matrix by interchanging first two rows. So 0 1 0 0 1 0 0 0 0 0 1 0 0 0 0 1 is the elementary matrix corresponding to that interchange operation, right? So for this E1, the second matrix can be written as the corresponding elementary matrix times the original A matrix, right? Now, the third one is obtained from the second matrix by multiplying a quarter to the first row of the second matrix, right? So, if I multiply a quarter to the first row of the identity matrix, then we get the corresponding elementary matrix. So this one. So for this E2 matrix, if I multiply E2 to the E1 times A, the second matrix, you get the third one. Okay, so when I perform some row operation, previously I used this arrow to imply the direction of the change. Now I can put this second matrix as a product of E1 and A to get the equality. The third matrix is a product of three matrices, E2, E1A. And please remember that matrix multiplication is not commutative, so the order of these elementary matrix is important. So you need to multiply E1 to A first, right? And then you multiply E2 for the scaling operation. And then the next operation is obtained from the third matrix by performing some replacement operation. You multiply negative A to the first row and then add it to the third row. So the corresponding elementary matrix will be, given the identity matrix, if I multiply negative A to the first row and then add it to the third row, then you get negative 8 in the third row first column, while all the other numbers in the third row are not changed. So this E3 will be the corresponding elementary matrix. So the fourth matrix is E3 times the third matrix. The third one is E2 times E1 times A. So if you multiply these, you get this matrix. So in this way, when I perform some elementary row operations, then we get this matrix. So let me call this guy by A star for simplicity. Then this A star is obtained from A by multiplying some elementary matrices, say EP. Then you get A star matrix. Okay? Right? So we arrive at this A star. And then beyond this A star, I performed column operation. So for example, I multiply negative 1 to the first column and then add it to the fifth column. So since I'm multiplying the identity matrix from the right and A is 4 by 5 matrix, okay? So if I call the corresponding the elementary matrix by F1, then given the 5 by 5 identity matrix, if I multiply negative 8 to the first column and then add it to the fifth column, the first row fifth column entry will be negative 8, and then you get this one. So this is your F1. Then this one, okay, the next matrix is obtained from A star by multiplying F1 from the right. right? And then you consider this. Oops, sorry. I multiply, I multiply the negative 1 to the first column and then add it to the fourth column, sorry. So if I do that, here, negative 1 and 0, that should be F1, sorry. And then I multiply negative 1 to the first column and then add it to the fifth column. So the corresponding elementary matrix will be F2. That will be 1, 0, 0, 0, negative 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and this one. Then for this F2, this one is the previous matrix, A star F1 multiplied by F2 will be this guy. Okay, so in this way, if you multiply, given this A star, if you multiply some elementary matrices, you get the D matrix, which is of this form. And since A star is obtained from A by this multiplication, what we have is this. Given A, if I multiply E1 up to, say, EP from the left and some other elementary matrices, say F1 up to Fk, you get D matrix. So this is the result of the theorem. Okay, right? So given A, if I perform some elementary row and column operations, you can always transform your A into a D matrix, right, of this form. And that means the each elementary row operation means the multiplication by some elementary matrix from the left, right? And then you perform elementary column operation, which corresponds to the multiplication by some elementary matrix from the right. So the theorem claims that if I have such a matrix, then by multiplying some elementary matrices from the left or from the right, you get this D matrix, right? And please note that all these elementary matrices are invertible. Okay. So from this, we have the following theorem. So given A, if I perform elementary row operations or column operations, in other words, if I am given this A, if I multiply some elementary matrices from the left and some elementary matrices from the right, you get D matrix. Okay. Now, and as I said, this E1 up to EP, they are all invertible matrices. So if you multiply invertible matrices, you get an invertible matrix. So if I call this guy by B, and if I consider this product on the right, and if I call this product by C, then B and C will be invertible, and D can be obtained by multiplying this B and C to A from the left and right. Right? So given A, we can always find some invertible matrices B and C corresponding to elementary row operations and elementary column operations respectively. And when you multiply those B and C from the left and right to A, you get this D matrix. Okay. Now, before I go to the next slide, what is the rank of D matrix? What do I mean by the rank of a matrix? By definition, the rank was initially defined by the rank of left multiplication operator, but later we derived some simplifying theorem which says given a matrix, the rank of a matrix is eventually the number of linearly independent columns, right? Now, given this D, what is the rank? These columns are just zeros, right? Those columns are just the zeros. And for these R columns, they are linearly independent. So this D has, note that this D has R linearly independent columns. So the rank of D will be R. Then what is the rank of A? From A, I obtained D, right? I obtained D and I just multiplied some invertible matrices, and the multiplication by an invertible matrix does not change the rank. So the matrix A will also have the rank R, right? So given A, if I transform A into some matrix like this D, then this D has rank 3. And that means A has rank 3. And actually, all the matrices appearing in this slide will have the same rank 3. Okay? So when I have this I3, I mean, if I obtain this D, okay, I can count the number of independent columns. So the rank will be D when I look at this D matrix, right? But I can see this, I can see, I can derive the same result even when I look at this A star matrix, right? Because first the 3 columns are linearly independent, right? And when I look at the other 2, they can be constructed as a linear combination of 3 preceding columns, right? I mean, first 3 columns are definitely linearly independent, right? And fourth and fifth columns can be constructed with respect to the first 3 columns. So that means I can see that the rank of A star matrix is 3, right? So if I interest in just the rank, I can stop at A star matrix. You don't have to go all the way to D matrix. Do you understand what I'm saying? So when I look at D matrix, it is clear, everything is clear, and the rank is definitely 3. But if I want to find the rank only, then I can find the rank when I look at A star matrix. right? Because the fourth and fifth columns do not increase the rank, because fourth column is a linear combination of first column and the second column. And the fifth column is a linear combination of the first three columns. So, so by looking at A star, okay, the rank will be 3. Okay? But I can see the rank even when I look at this matrix, right? When I look at this, first three columns are definite. So when I look at this, the red one, the first three columns are definitely independent. So I can see that they are linearly independent. So I can stop at this red box and then I can claim the rank is a 3, right? But you may have some doubts. So let us go back to this example later, okay? But anyway, definitely when I look at A star, then you can definitely say the rank is a 3, right? So please remember this. So we considered this. Now, the reason why I say if I look at the red box, the matrix in the red box, the rank is a 3 because of this corollary 2. So let us look at this one. So suppose that suppose that A is any m by m matrix, then the first claim, rank of A transpose will be the same as rank of A. Okay, so why do I have this? So by the first corollary, given A, we can transform A to D by performing elementary row operation, which introduces B, and some elementary column operation, which introduces C matrix. And please note that B and C are all invertible matrices. Now, what is the shape of D? D consists of I sub R identity matrix 0, 0, 0. Okay? Of course, they are all zeros. And this is an m by n. And I sub R is an I by R matrix. Okay? So, given this, if I take the transpose of D, then that's the transpose of the product. And by the property of the transpose operation, we get C transpose, A transpose, B transpose. Okay? Right? Then, what does that mean? What is the meaning of this? Given A transpose, if I multiply some invertible matrix, C transpose will be invertible because C is invertible. And if I multiply B transpose from the right, then this B transpose is invertible. Okay? Then rank of A transpose will be, okay, rank of D transpose matrix, rank of D transpose, and this is C transpose and B transpose are invertible. And moments ago, I mentioned that the multiplication by an invertible matrix does not change the rank. So multiplication by this C transpose or B transpose does not change the rank, right? But anyway, the rank of A transpose is this. So rank of A transpose is the same as this, and this is just the D transpose matrix, right? So let me mention one more time. Given A transpose, multiplication by invertible matrices do not alter the rank, so the rank between these two will be the same, but this product is just the D transpose matrix. Now, what is the D transpose? If this is on D matrix, then D transpose will be the transpose of I sub R, and then the transpose of O2 will come here, and the transpose of O1 will come down here, and then we get O3 transpose. And the transpose of I sub R is meaningless because I sub R is an R by R identity matrix. Its transpose is the same as I sub R. So, given this D transpose matrix, these R columns will be linearly independent, and that will give you the rank. So given this T transpose, the rank will be still R. Okay, so rank of A transpose is the same as rank of D transpose, and that will be R, and this R was the rank of A matrix. So the transpose does not change the rank. Okay, now what was the meaning of rank of A? That was the maximum number of linearly independent columns in A matrix. Okay, that was the one of the theorems we considered. Now, if I apply that theorem to A transpose, then this rank of A transpose will imply the maximum number of linearly independent columns in A transpose matrix. Columns in A transpose will be the same as the rows in A matrix. So the transpose, if the transpose does not alter the rank, then the rank of A will be the maximum number of linearly independent rows in that matrix, right? So that is the statement B. The rank of any matrix will be the maximum number of linearly independent rows. Okay, and then one more step. This the number of maximum number of linearly independent columns in A. That was the dimension of the span of columns. So I need more space. So this will be the dimension of span of columns in A matrix, right? Now the rank can be counted by using the maximum number of linearly independent rows in A. So that means the rank will be the dimension, the rank will be the dimension of the span of the rows, the space generated by the rows. That is just the, so this is the span of the rows in A matrix. Okay, so the number of linearly independent rows, okay, and the number of linearly independent columns are the same. They are equal. Let me go back to this matrix. So when I look at the three matrix, the matrix inside the red box, I mentioned that three columns are linearly independent because when I look at three rows in this matrix, they are linearly independent. Due to these zeros, three rows are linearly independent. But if I add the fourth row, since the fourth row is the zero row, if you include the fourth row, then those four rows will be linearly dependent, right? So first, the three rows are independent because the one is not a multiple of the other, right? But I mean, the first row is not a linear combination of the second and third rows because second and third rows have zeros in the first column, but the first row has a non-zero entry 1, right? So first row is not a linear combination of second and third rows. And second row is not a linear combination of the third row. So all three rows are linearly independent. So when I look at the matrix inside the red box, the three rows are linearly independent, right? So the rank is 3. So if I need to find the rank of a matrix, you can stop at the red box because that will tell you that you have only 3 linearly independent rows. So that will be the conclusion here. So the rank of a matrix was previously the maximum number of linearly independent columns. Now, since the transpose does not change the rank, the maximum number of linearly independent rows will be also the rank, and so that means that's the dimension of the subspace generated by the rows. Okay. Okay, so the C is a trivial, but so before I go to the next part, let me just mention one more thing. Okay, so here A is on M by N matrix. M by N matrix. So span of columns in A is a subspace in Fm space. Space generated by rows in A matrix is a subspace of Fn space. Please remember that L sub A is a linear transformation from Fn to Fm space. The space generated by the columns in A is a subspace of Fm space. Okay, but this space generated by the rows in A are some subspace in Fn space. But this corollary says, even though they belong to different spaces, their dimensions are the same. So dimension of span of columns will be the same as the dimension of the span of rows in A matrix. Okay, their dimensions are the same, but those two spaces belong to totally different spaces. Okay, so please be careful when you read these statements. Now, every invertible matrix is a product of elementary matrices. Well, if A is invertible, then the rank, okay, if A is invertible, then and that means A is first of all square n by m matrix. So if A is invertible m by n matrix, then the rank must be n. And then what does that mean? Then rank is n. Rank of A is the same as rank of D, right? So this must be the rank of D, okay? And D is on n by m matrix. So this D is on n by n matrix, and the rank just counts the number of columns of the identity matrix in the upper left corner, right? If that matrix in the upper left corner has only R columns, then the rank of D will be R, right? Now, the size of this D is n by n, and the rank is n, then that means this D is filled by I sub n. There is no 0, 1, 0, 2, 0, 3 in this case, right? So given A, when I perform elementary row operations and column operations, you get D matrix, and this D must be an n by n identity matrix. Okay, so we get this identity here. And since B and C, those B and C, please remember that this B and C are products of elementary matrices. Okay, so B is a product of these elementary matrices, and C is also a product of elementary matrices. Okay, and so that means given I sub n, when I multiply E sub p up to E sub 1 and A and G sub 1 up to G sub q, you get the identity matrix. And please note that E1 up to EP and G1 up to GQ are all invertible. So if I multiply their inverse matrices, then A is the product of these. Actually there was an identity matrix between these two, but since you are multiplying some matrices to identity matrix, this identity matrix is meaningless. So A can be written as a product of these inverses of elementary matrices. And please note that the inverse of elementary matrix is also the elementary matrix. So this A will be actually a product of elementary matrices. Okay? But okay, so this is the formal proof, but let us go back to my example. So suppose that I have on, if my A was on n by n invertible matrix, if, okay, then if A is a 4 by 4 invertible matrix, then when I arrive at the red box, you cannot have a row of zeros, first of all, right? Why? Because in that case, the rank of the matrix inside the red box will be 3, but I have a 4 by 4 invertible matrix, so the rank must be 4, right? So the rank must be the number of linearly independent rows, right? So probably if I perform some elementary row operations, then your A will have some non-zero value here in the fourth row, fourth column, if A were invertible, right? And then I can proceed a little bit more to change this value to 1. And then if I perform some elementary row operations, I can convert all these numbers to zeros. So when I perform the elementary row operations, the matrix corresponding to A star will be the identity matrix. In other words, if A were a 4 by 4 identity matrix, then probably this A star will be the 4 by 4 identity matrix. In other words, I do not need these column operations, right? So if A were an n by n invertible matrices, then actually I do not need these guys. They don't need this. I don't need them. Okay? But anyway, if I use the previous results, then at this point, I might need G1 inverse of the GQ inverse. But in practice, if my A were an invertible matrix, then I can obtain the identity matrix by performing the elementary row operations only. I do not need elementary column operation. Anyway, okay. Now, in theorem 3.7, suppose that I have two linear transformation, T and U. T is a linear transformation from V to W, and U is a linear transformation from W to Z. Okay. And suppose that they are linear transformations, and let A and B be matrices such that the product of A times B is defined. That means, what is the meaning of this? That means the number of columns in A will be the same as the number of rows in B matrix. Okay. In other words, okay. So yeah, that is the meaning. Okay. Anyway, so A and B are matrices representing. Okay. Yeah. So A and B. Yeah. Now, the first statement in the theorem is the rank of this composite U and T cannot be greater than rank of U. Okay. This is very important inequality, but okay. So rank of UT, okay, will be cannot be greater than, is less than or equal to rank of U. So let us prove this one first. So let us prove this. So definitely, okay, so T is a mapping from V to W, and U is a mapping from W to Z. Okay, so the range of T is definitely included in W space, right? We have, yeah, V, W, Z. So here, so T is a mapping from V to W, and range of T is included in W. So range of T is included in W, right? And U maps W to Z. So here is the Z space, and the range of U will be here. So that's the image of whole W space. And if I consider this range of T, that will be contained here, right? So range of this composite is the image of T of V, which is this purple one inside the W, okay? And so that is, so this all of T is this W set, and this W is included in W. So W is bigger than this purple one. So the image of U, image of this purple under U will be included in the image of whole W space, right? So the range of this composite will be included in the range of U space, U mapping. So rank just counts, the rank represents the dimension of this space. So that will be smaller than the dimension of the range of U. That is the rank of U matrix, rank of U mapping. So rank of the composite of U and T cannot be greater than rank of U. Okay? So that's the first statement. Okay? If that is the case, if that is the case, then rank of this product of two matrices is defined by the rank of this left multiplication, and this L sub AB is just the product of the composite of these two. Then by A, the composite of these two cannot be greater than rank of this guy, which is rank of A. So rank of A times B cannot be greater than rank of A. And if that's the case, rank of AB is the same as rank of its transpose. And the transpose of A times B is B transpose times A transpose. And then by applying this C again, what is the statement to C? Rank of A times B cannot be greater than rank of the one on the left, right? But now here I have rank of B transpose and A transpose. One on the left is B transpose. So this cannot be greater than rank of B transpose, and the transpose is not change the rank. So rank of B transpose will be the same as rank of B. So if C is correct, B will be correct. Now to prove B, suppose that I have some basis for V, W, and Z spaces. So let me call them as alpha, beta, and gamma respectively. Okay, and let me use A prime to denote the matrix representing U with respect to beta and gamma, and let me use B prime to denote the matrix for T with respect to alpha and beta. Then this product will be a matrix representing this composite with respect to alpha and gamma. That's what we learned before. So the rank of this is defined by rank of this matrices, product of the matrices, and by D, the rank of this product is cannot be greater than rank of B prime, and rank of B prime is the same as rank of T. So we go back this. So the statement A or statement B, they say if I consider the composite, of two mappings, dimension of the composite cannot be increased, right, from the original mapping. Given T and U, you have two mappings, right? T and U. They have their own rank, meaning the range of these two mappings have a certain dimension, right? And that dimension cannot be increased by the composite. Okay? Or you may say, if you multiply two matrices, if you multiply two matrices, the number of linearly independent columns cannot be increased by multiplying two matrices. But so if you consider some data science these days, there are some people, some papers, which claims that when they do something, I mean, they consider some composite functions. They say they can introduce more linearly independent information, which does not make any sense. Okay, because of this theorem 3.7. When you consider the composite of two mappings, you cannot generate a new theorem. There can be no news. There can be no news from the composite. Or when you multiply two matrices, you cannot generate a more linearly independent columns. Okay, so that is the meaning of theorem 3.7. The composite, okay, of mappings that corresponds to some layers in artificial intelligence. Okay, if you consider some models in deep learning, okay, if you introduce more layers, that does not increase the dimension of the original information. You cannot produce new one, okay, from the initial database. I mean, from the initial data. If initial data is, say, three-dimensional, then whatever you do with your artificial intelligence or deep learning or whatever, the number of linearly independent vectors cannot be greater than 3. Okay? But some people claim that, I mean, I read some papers in deep learning that by using certain artificial intelligence model or certain deep learning model, we can introduce new data, which does not make any sense, which is wrong. okay, because of this theorem 3.7. Anyway, in example 4, when I look at this A matrix, okay, these two rows are linearly independent, definitely, because one row, the first row is not a multiple of the second row, and second row is not a multiple of the first row. So that means these two rows are linearly independent, so the rank is 2. That means even though there are 4 columns in A matrix, only 2 are linearly independent. The other 2 are redundant. Okay. When I look at the matrix B, okay, the rank is 2 in this case, because as you can see, the first, third, and fourth columns are redundant, right? So that means only 2 columns will be linearly independent. So the rank of this A will be 2. Then that means when I perform some elementary row operation, so if I perform some elementary row operation, then you have some 2 non-zero rows, and then the third row will become just the 0 rows. Okay. Actually, you get 1, 3, 1, 1, and then you get 0, -3, 0, 0, and 0 rows. Because the rank is 2, not 3. Given this C, given this A matrix in C, if I perform elementary row operation, you get this. So that means these 3 columns are linearly independent. Okay, or these 3 rows are linearly independent. Okay, questions? So before I go to the next part, so given some m by m matrix, the rank of A cannot be greater than the number of rows and columns, right? So what I can tell you is the rank cannot be greater than the minimum of m and n, right? So this is a very simple fact, but sometimes it is useful. So when I look at this matrix, the rank of A cannot be 4, right? So that means if I have this m by m matrix, and if n is greater than m, so if n is greater than m, then at least the rank will be at most m in that case. So the rank is at most m. And that means I can eliminate n minus m columns. They are redundant. The information carried by those n minus m will be redundant. Okay, since I don't have sufficient time, okay, let me just introduce the definition of the augmented matrix. If I have 2 matrices, m by n matrix A and m by p matrix B, so they have the same number of rows. Okay, then when I say the augmented matrix, that means then I just combine these two. So you have A matrix and B matrix with the same number of rows. Then when I say they're augmented matrix, that means that I'm just combining this big matrix, okay, big matrix with m rows, and the number of columns will be n plus p. So this new matrix, okay, combining these columns of A and B, that matrix will be called the augmented matrix. Okay, and then let me call it a day here, and then let me continue, okay, next time. Okay, anyway, if you have any questions, please email me. Thank you for listening, and see you next time.